And happy Friday. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. Okay, so today we're going to go on and cover section 11.4. I mentioned to Karina before you got here, Antonia, that this is a 3-day weekend, so there's no school on Monday. All right, just in case you weren't sure about that. And let's go ahead and get started. Would you agree that 2 cubed is equal to 8?
Yes.
And that 2 to the 4th power equals 16.
Yes.
But 2 to what power would equal, let's say, 10? Well, hopefully you would see that it must be some number between 3 and 4, 3 point something. And I suppose through trial and error, you could take 2 raised to the 3.1 power, 2 raised to the 3.2 power, 2 raised to the 3.3 power, on and on and on. And through time, you could get closer and closer to an exact answer. But that's not a very efficient way of doing things. So the question is, when we have an equation and the unknown is an exponent, how do we go about solving for that exponent? And the answer, at least one of the answers, is something called a logarithm. And that's what we're going to be looking at today. If I have the following equation, 2 to the x power equals 10, that is equivalent to the equation log base 2 of 10 equals x. Now, if you've never seen logarithms before, this is like, what's going on here? Don't panic. That's what we're going to be looking at these next few days. But the point is, by writing it in this form, I've isolated the variable, the thing I'm trying to solve for. So if I could then go and say, well, what's log base 2 of 10? And we do have a way to do that, and we'll be looking at that. I could get the answer to my question as to 2 to what power equals 10. Okay, so what I've done here, let's see here, is created an equation. Actually, what I want to do is this. I want to make a two-way arrow and say, this is an exponential equation. This is what we call a logarithmic equation, but they are equivalent, okay? Now, there's a pattern. If we look at the first equation, 2 to the x power equals 10. 2 is the base, and x is the exponent, right? So 2 would be what we would refer to as the base. On the right side, this equation, the way we say it is log base 2 of 10. So on the right side, the logarithmic equation, the 2, is also called the base. Notice on the left side, we've got x connected with the 2 and 10 off by itself. On the right side, 10 is somehow connected to the 2 and the x is off by itself. Now this is not 2 to the 10th power. So it's not exactly the same form as the other side. We say log base 2 of 10. But what I want you to notice is that the bases are the same in both cases. And the numbers, the other two, change places, okay? So what we're going to be doing now is practicing going back and forth between the two forms, taking a exponential equation, writing it as a logarithmic equation, taking a logarithmic equation, writing it as an exponential equation. The reason that it's important that we know how to do this, to go back and forth between the two forms, is not always, but most of the time, if you're trying to solve an exponential equation, you change it to a logarithmic equation. Likewise, if you're trying to solve a logarithmic equation, you change it to an exponential equation. So let's look at some examples of this. Give me a second here to get to the page. Let's say we have the following equation. Log base 7 of 7 equals 1. So the base is 7. Log base 7 of 7 equals 1. So writing this logarithmic equation as an exponential equation, it would be 7 to the 1 power equals 1. And that is a true statement, isn't it? 7 to the 1 power equals 7. Okay. So that's the exponential equation form of this logarithmic equation. Let's look at another one. Log base 10 of 100 equals 2. So the exponential equation would be 10 squared equals 100. The bases are the same. The other two numbers change locations. We doing okay so far? All right. Well, I'll continue then. Log base 6 of 1/36 equals -2. The exponential equation equivalent, 6 to the -2 power equals 1/36. Log base 8 of the cube root of 8 equals 1/3. Exponential equivalent, 8 to the 1/3 power equals the cube root of 8, which would be the same thing as 8 to the 1/3 power, right? Okay, now this one says log 0.01 equals -2, but there's something missing. All these other problems had a base 7, base 10, base 6, base 8. This one doesn't have a base written. That's because log base 10 is used so frequently that mathematicians decided to call that common log, and to be more efficient, they're not going to put the base. So LOG is the notation for log base 10. If you have your scientific calculators handy, if you look at it, you'll see that in the first column, okay, right up here, the second button says LOG. So what you've got is you've got this blue button that says second, and then right below it, it says LOG. Do either of you have your calculators with you?
Yes.
And you'll notice that the second function of that second button is 10 to the x power, which can help remind you that this button, LOG, means log base 10. Okay? So having said all of that, this is the same thing as that. They just leave off the 10 because that's the most common base. So they say, let's not bother with the 10. Doesn't save a whole lot of work, but that's the way they do things. Okay. Now, so this would be 10 to the -2 power equals 0.01. But from here, you'd have to remember that there's a 10 there to get 10 to the -2 power is 0.01. All right. Any questions there? So the takeaway from this is log means log base 10. Now, as I pointed out, we do have a log base 10 button on our calculator. So let's do this. Let's put log base 10 of 0.01 in our calculator and see if we do in fact get -2. So I turn my calculator on. I push the log button and it looks like this. I put in 0.01. Oops, hang on here. 0.01. Close it up with a right-hand parenthesis and then push equals, and I get -2. So again, if you have your calculator with you, try that, make sure you're getting -2, and if you aren't, now would be a good time to let me know.
I have it.
Okay.
Let me see. I'm working on it. Let me see.
Okay, that's fine.
I get 1.02. Maybe I'm doing something wrong.
Okay, do you have the same calculator that I'm showing you?
Yes.
And you see where the button that says LOG?
Yes.
All right, so with the calculator cleared, push that button.
Okay.
Does this appear?
Yes.
Put in 0.01 and then close it up with a right-hand parentheses and push equals.
Got it.
Does it work?
Yep. It worked.
Okay,
Thank you.
we're good to go. Let's continue. All right, let's see here. How about this? X equals log base 9 of 81. So that would be 9 to the x power equals 81. Changing the logarithmic equation to the exponential equation. Okay. N equals log base b of r sub 1. So that would be b to the n power equals r sub 1. And finally, log base m of p equals 101. That would be m to the 101 power equals p. So this is the log, this is the exponent form of the equations. All right with that?
Yes.
Now we're going to go the other direction. We're going to take exponential equations and rewrite them as logarithmic equations. So 8 squared equals 64. The base is 8, so log base 8 of 64 equals 2. 10 cubed equals 1,000. Log base 10 of 1,000 equals 3. Or we could write it like this. Log of 1,000 equals 3 because the base 10 is assumed if nothing's written there. Okay. Doing all right with these examples?
Yes.
All right, here's some more. 3 to the -4 power equals 1 over 81. That would be log base 3 of 1 over 81 equals -4. One third to the -3 power equals 27. Log base 1/3 of 27 equals -3. M to the n power equals p. Log base m of p equals n. B to the r power equals 2/3. Log base b of 2/3 equals r. (12) to the -2.6 power equals n plus 1. Log base 12 of the quantity n plus 1 equals -2.6. And I want to point out that I needed to quantify that so that that whole thing becomes the thing you're taking the log of. If I wrote it like this, that would imply log base 12 of n plus 1, and that's not what you want. You want log base 12 of the quantity n plus 1. Okay? So there's practice in going back and forth between logarithmic equations and exponential equations. Now, we're going to solve some equations rather than just converting them. I have log base x of 81 equals 2. All right. So to solve this logarithmic equation, the first thing I'm going to do is convert it to an exponential equation. And that would be x squared equals 81. Are we okay with that conversion?
Yes.
Now, let's solve this. Well, this is set up perfectly for the square root property. So let's take the square root of both sides. So we come up with x equals plus or minus 9, right?
Yes.
However, there's a problem. The correct answer is just x equals 9. It can't be negative 9. Well, how do we know that? Well, let's go back in time to yesterday when we looked at, let's see, exponential equations, y equals b to the x. And we talked about that b had to be greater than 0, but b could not equal 1. Do you remember that?
Yes.
And we talked about that x could be, let's see, the x values was all real numbers. So we'll say negative infinity to positive infinity, and that y had to be greater than 0. Okay. Do you remember all that when we were graphing? So
Yeah.
basically your domain and your range. All right. Now, if we take y equals b to the x, it has all of these conditions imposed on it. If we rewrite that as log base b of y equals x, this b is the same as that b. This x is the same as that x, and this y is the same as this y. What does that mean? Well, let's go back to b. B has to be greater than 0 and not equal to 1, right? So that means right here, log base b, b has to be greater than 0 and not equal to 1. X, the exponent, can be any real number. So the answer over here of the log can be any real number. So a log can have a positive answer, a log can have a negative answer. But this has to be greater than 0, which means the thing we take the log of has to be greater than 0. Okay, so if I have log base b of y equals x, b has to be greater than 0 and not equal to 1. Y has to be greater than 0, but x can be any real number. So let's take that and go back here. That's the base. It has to be.
Has to be greater than 0.
Right. So based on that, we would throw out the negative, even though it's a solution to this equation. All right. Okay. Let's go on. Another example. Log base 7 of x equals 0. So this would become 7 to the 0 power equals x. Well, what is any number other than 0 raised to the 0 power? So 7 to the 0 power equals what?
1.
1. So x equals 1. Log base 7 of 1 equals 0. 7 to the 0 power equals 1. But our solution is that x equals 1. Okay. You good to go on?
Yes.
All right. log base 4 of 16 equals x. To solve for x, we'll write this as an exponential equation. 4 to the x power equals 16. Now, exponential equations are one-to-one functions. Logarithmic equations are also one-to-one and functions. Because of that, if we have an equation like this, 4 to the x power equals 16, if I can take the right side of the equation and write it so that it has the same base as the left side of the equation, then the exponents would be equal. So if 4 to the x equals 4 squared, then x equals 2. 4 to the x equals 4 to the 2, therefore x equals 2. We okay with that?
Yes.
All right. Let's see here. Log base 3 of x equals -4. So we get 3 to the -4 power. 3 to the -4 power equals x. Well, 3 to the -4 power is 1 over 3 to the 4th is 1 over 81. So x equals 1 over 81. Okay. Good to go on?
Yes.
All right. Log base x of 1/1000th equals -3/2. So x to the -3/2 power equals 1 over 1,000. I need to solve for x. When you have a power raised to a power, for instance, let's say I've got 2 cubed to the 4th power, you multiply the exponents, right? So I could take both sides of this equation and raise them to the -2/3 power. Why would I do that? Because now a power raised to a power, we would multiply the exponents. -3/2 times -2/3 would be a +1. So this would be x to the 1 power or just x. Okay. So now I have to deal with the right side. 1 over 1,000 to the -2/3 power would be 1,000 over 1 to the +2/3 power, which would just be 1,000 to the 2/3 power. Okay. But 1,000 to the 2/3 power would be equal to 1,000 to the 1/3 power squared. In other words, I could do the root and then the power, but 1,000 to the 1/3 power, the cube root of 1,000 is 10, and 10 squared is 100. So all of this, x equals 100. So log base 100 of 1,000th is -3/2. Did I lose you there somewhere?
No.
Okay, we good to go on? All righty, I'll take that as a yes. Let's see here. About this. Log base 4 of 8 equals x. So 4 to the x power equals 8. Well, I don't know how to take 8 and write it as 4 to some power, at least not off the top of my head. But I could do this. I could take both 4 and 8 and write them as powers of the base 2. So here's what I'm going to do, okay? I'm going to take 4 and write it as 2 squared. So 4 to the x becomes 2 squared to the x power. But now a power raised to a power, you'd multiply the exponents. So 4 to the x becomes 2 to the 2x power. Why would I want to do that? Because 8 is 2 cubed. So now I've got 2 to the 2x power equals 2 cubed. Therefore, 2x equals 3 and x equals 3/2. So log base 4 of 8 equals 3/2 because 4 to the 3/2 power equals 8. You okay with that?
Yes.
All right. The next set of problems say evaluate each logarithmic expression. So we've got log base 2 of 8. All right. So I need to figure out what log base 2 of 8 equals. Well, I don't know what it equals, so I'm going to say it equals some unknown box. Okay. Well, now I could take what has become a logarithmic equation, and I could rewrite it, maybe a little nicer than that, as an exponential equation. So 2 to the box power equals 8. But I could go further and say, well, 8 is 2 cubed. So now I have an exponential equation. 2 raised to the unknown box power equals 2 to the 3rd power. So the box equals 3. So log base 2 of 8 is 3 because 2 cubed equals 8. All right with that?
Yes.
Okay. Log of 1 over 10,000. Evaluate it. Well, we could say it's equal to some unknown box. Not only that, but since it's just plain old log, there's an implied base 10, right? So now changing it to an exponential form, I get 10 to the box equals 1 over 10,000. Ten thousand is 10 to the 4th power. I could take 1 over 10 to the 4th power and write it as 10 to the negative 4 power in the numerator. Why do I need to do that? Because on the left side, I've got 10 to some power. So on the right side, I need 10 to some power. So now the box equals negative 4. Okay with that?
Yes.
Let's do this. Let's go back to the calculator. And let's see what we get. We're going to use the LOG button, log base 10. So push that. And then inside 1 divided by 10,000, close it up, push equals, and you should get negative 4. So try that and see if that's what you get.
Got it.
Excellent. Okay. Now we're just going to evaluate specific logs using the calculator. So I've got log of 0.57. So again, I'm using the LOG button, log base 10. So that, and then I put in 0.57, close it up, push this equals. It says, give answers to 4 decimal places. I get negative 0.244, 4412. That would be the 4th place. The 2 would round down. So negative 0.2441 would be the correct answer. We getting that all right?
Yes.
Okay, let's do log of 375.876. So log of 375.876. I'm getting 2.575044597. There's 4 places, the 4 rounds down, so 2.5750. All right with that? Oh, my bad. Now, you getting that okay?
Yes.
Yes.
All right, now we're going to solve some equations using our calculator. It says log of x equals 2.8945. Use a calculator to solve the equation, round answers to 4 decimal places. So keep in mind, there's an implied base 10 there. So this means that 10 to the 2.8945 power equals x. Well, I can put that into my calculator. Now, there's 2 different ways I can enter a 10 raised to some power. I can use the way we would have used before, 10, the little caret key, and then 2.8945. Or notice the LOG button. The second function key is 10 to the x. So I could do it this way, or I could go second and then the LOG button, which would then give me, let's see, second LOG, second. And when I push equals, I get that. Actually, not when I push equals, when I go second and then the LOG button, I get 10 to the, and then I'd put the 2.8945 close parentheses, 2.8945 equals. Okay, so I can either use this notation or this notation. Either way, you okay with that? I'm getting as an answer 784.3321189. So right there would be 4 places. The 1 would round down. So 784.3321. All right, okay with that?
Yes.
Okay, now we have an application problem. It says stocking lakes, not the kind of stockings you wear and not stalking somebody, but putting fish in a lake. But like the game department will stock a lake, they'll put in fish. It says a farmer stocked a lake on her property with 75 sunfish. She was told that with the proper oversight, the sunfish population could be approximated by the logarithmic function f of t equals 75 plus 45 times the log of the quantity t plus 1, where t is the number of years since the lake was stocked. Find the number of sunfish she can expect in the lake in 2.5 years. So at the beginning, when t is 0, we would get 75. All right. So then what happens after that? Well, if t is 2.5, how about if we use 2.5 instead of 2.5? So that's going to be 75 plus 45 times the log of 2.5 plus 1. Combining the t and the plus, or putting 2.5 in the place of t, that would be 75 plus 45 times the log of 3.5, right? 2.5 plus 1. So on your calculator, 75 plus 45, and then log 3.5, close up the parentheses, equals, and I get 99.48. So the nearest whole sunfish would be 99. So we'll say about 99 sunfish. Okay? We all right with that?
Yes.
Here's another example. Children's height. So how tall a child is. The logarithmic function h of a equals 29 plus 48.8 times the log of the quantity a plus 1 gives the percent of the adult height of a male child a years old. If a boy is 9 years old, what percent of his adult height will he have reached? So h of 9 would be 29 plus 48.8 times the log of 29 plus 1, which is 29 plus 48.8 times the log of 30. So on our calculator, 29 plus 48.8, push the log button, put in 30, close it up, and I get, hang on here. Okay, what did I do? Oh, what did I do wrong?
I thought that in the parentheses it was supposed to be 9 plus 1, not
Yes,
two
it
nine.
is. And the reason I was suspicious is my answer was 101%. Let's try that. Yeah, I grabbed the wrong number. 29 plus 48.8 log of 10. You know, it's funny, as I was doing it, I thought, well, that's interesting that the same number goes here as here. That's not what was supposed to happen. 77.8. So that would be the percent. So what they're saying is, on average, a 9-year-old boy has reached 77.8% of his adult height. That doesn't mean that will happen for every boy, but on average. So like if you take 10,000 boys that are 9 years old and measure how high they are, and then you come back when they're adults, kind of thing. Okay?
Okay.
All righty. Well, that's all I've got for you today. So I'm going to go ahead and stop the recording.